In this video, I spend 8 hours photographing my favorite galaxy, the Whirlpool Galaxy, across 4 nights, testing the limits of my Dwarf 3 Smart Telescope. Now that I've collected all that data, it's finally time to start processing. For this workflow, I'll be using Cyril. Although, take everything I do with a grain of salt, because I'm still a beginner to this software. First things first, I convert all 1,300 frames in Cyril, putting them all together, even though they were taken on separate nights. After a long time of processing, I ended up with this as my image. Thought the difference would be a little more dramatic, didn't you? I initially thought so too. Well, the reality is, after you reach a certain point, adding more hours doesn't really improve the image that much overall, especially when you're a beginner at astral processing, like I am. Many people are deceived into thinking that 4 times the amount of exposure means 4 times better quality of an image. However, the math actually works a little bit different than that. The image's improvement by exposure time is not linear like a lot of people would expect. In reality, image quality improves by something called the signal-to-noise ratio, or SNR. So in order to know how much your image is improving, you need to take the larger exposure time and divide it by the smaller exposure time, and then take the square root. This means that the true improvement is 2 times rather than 4 times. For example, if I were to do a 4-hour exposure instead of a 2-hour exposure, then that would be an improvement of 1.41 times. If I went for 6 hours, then the image would be 1.73 times better. And we all know that if I went for 8 hours, then the image would be improved by 2 times. Thus, it should only improve by 2 times, which isn't really much considering how many hours I put in. In order for an image to look 4 times better than the 2 hours of exposure, it would have to have 32 hours of exposure. Not to say that an improvement of 2 times is unimportant, but to say that it's too minimal for targets like the Whirlpool Galaxy that are small and faint, compared to other celestial objects like perhaps the Orion Nebula or the Andromeda Galaxy. Now those would certainly improve from 8 hours of integration, while I believe that the Whirlpool Galaxy may have reached its limits for my scope. Another thing that may have hindered the image's quality is that I took all of the 8 hours on separate nights that were far apart from each other. This means that all of the data would be quite varied in quality, because on some nights there may have been less atmospheric turbulence or less water vapor in the air, like, haze. Meaning that the quality on the images varied a lot, which means that when you put it all together into one 8-hour result, it could actually bring down the image quality rather than bring it up. Because my first initial 2-hour exposure was a lot higher quality than my remaining 2-hour exposures. Meaning that single 2-hour exposure would have actually been better on its own. When I went into this project, I had already learned the math behind the signal-to-noise ratio. Even then, I expected 2 times better to be a lot more dramatic than it was. Maybe the image would have been better if I had higher quality frames, better processing, or maybe if I really have stretched the limits of my smart telescope. What I learned is that with processing, conditions, and the telescope itself, one person can get a better looking result with a 2-hour image taken under good conditions and processed well, while another can spend 8 hours on a target, process it decently, and still end up with an image that doesn't look as good because of lower quality data or other limitations. In conclusion, more integration time doesn't always result in a dramatically better looking image, even though it is still a crucial aspect of astrophotography. That said, this probably isn't the final version of this image. As I gain more experience with processing, I may come back to this data in the future and see if I could bring out more from it than I was able to this time. Perhaps the Dwarf 3 would benefit more from long integration times on larger and brighter targets, such as Andromeda or the Orion Nebula. But that's a project for another day.